In this tutorial, we are going to talk about how we can do hypothesis testing of discrete variables in R. In the previous tutorial, you saw that how we could do hypothesis testing of continuous variables. So that was one way of doing it. In this in this particular lecture, we're going to see how we can do hypothesis testing of discrete variables or categorical variables. We have already alluded you to the fact that we have discussed the basics of hypothesis testing, setting up a 2x2 matrix, how we can take information, how we can take data from our experiments, putting them into tables, and then analyzing them. So those things can be kind of overlooked and not be repeated. And here I'm going to show you some very simple tests that can be done, and I will run you through a set of actual demonstrations on a data set to make sure that you can do those things. So in the in the next slide, let me give you a quick introduction as to who I am, and then we get underway. As you know, my name is Arindam Basu. I am at the University of Canterbury at Christchurch, New Zealand, and this is part of the E-Pathshala of the Ministry of HRD of India. And let's move on to doing some learning objectives. In the learning objectives of this, what are we going to learn as a result of this? So you're going to learn a few things. The most important thing, of course, is this, that we'll be using R. So there are certain R functions, there's some R routines, the libraries, and things that are really useful for hypothesis testing of categorical variables or discrete variables. The first requirement of when you deal with categorical variables is, of course, to understand that there are categorical variables in a data set, and you know them by using the type of function. That's very, very useful. The other thing, which is very important when you use categorical variables, is to create tables. So let's go bivariate tables, and we're going to deal here with only very simple two variables at a time. When we deal with two variables at a time, that kind of an analysis is known as bivariate data analysis. So we take one variable as the outcome variable, the other variable as an explanatory variable, and what we do in the process is we kind of take a look at one variable over the other, and we run some simple tests. This is the basic motive of working with discrete variables or categorical variables and setting up hypothesis testing framework. So we'll take a look at a couple of ways in which you can set up tables, and you can manipulate tables as well. And you will need to write a few functions that by now you should be familiar with writing functions. And when you write functions, you can actually catenate or bind the different tables together so that you can have a good representation of the raw numbers and counts as well as the percentages for the tabular data and for tabulation. So cross tabulation is a very important aspect of table formation and discrete data calculation. Once you have tabulated the data sets, then you are in a better position to then subject them to hypothesis testing. And we've got a few things on which we are going to test our hypothesis. We shall run tests like Fisher's exact tests and a chi-square tests. and we'll briefly touch on them, and we'll examine them by using a chi-square test to see whether you can, what can you do about them. So we'll do chi-square tests of significance or chi-square tests of independence. Then after I have demonstrated that you can do these things, I will run you through a worked out example which you will be able to replicate yourself, or you can take other data sets and replicate them yourselves to see how these things can be done and what are the things that you should need to do. One way to practice, of course, is to take continuous variables from your data sets, convert them to categorical variables, and then run tests of association or tests of independence with the categorical variables. That's a good thing to do because then you can get some hands-on practices and hands-on ways in which you can learn quite a few things. And then lastly, we'll summarize everything that we have learned here. So to recap, what we're going to do is we're going to read some data, then we're going to create some tables, and I'll show you how you can use the Fisher's exact tests and the chi-square tests, and then some association statistics that are quite useful. And then I'm going to run a full-scale example that will help you to run the most important concepts in this example. So the first thing that we need to do is to read and set up our data, and actually we'll be using a number of different data sets. One of the ways in which you can do that, of course, is to use our own built-in data, which are like data sets. So you could type data, and then depending on the library that you have set in here, you can then read these things, right? So we'll do that first. We'll read and set up some data. So the first one that we're going to do is we're going to call in a library called MASS, that is Modern Applied Statistics with S. This package was written by Brian Ripley and John Venables. And this is a very useful package to load in your R library, R profile. And this usually comes, I think, preloaded now with the R installations, the ones that you use now. And once you do this, then mass has got a function called xtabs, which you can also read as crosstabs. So it helps you to do cross-tabulation of data. We have made the xtabs function before in that module where we were describing categorical data. And what cross-tabulation did was that at that time you could take two or more variables, stitched them together, and put a tilde mark so that the crosstabs would then create cross-tabulations amongst those different variables, and using using the data in which those variables were present. And then what you would like to do is to keep that crosstab product or create a matrix out of that, although that's not entirely needed, because I will show you that there is one other way in which you could actually print the results of that cross-tabulations. However, there is a reason why I would prefer that you save the output of that cross-tabulation as a matrix. Because if you save the product of it as a matrix, or if you run what is known as an F table on that cross-tabulation product, you will see that instead of giving you a neat and complete representation of the raw count and the row-wise representation of the contents of the table or column-wise percentage counts or percentage tabulation, all it gives you are the labels of the variables that you put into it and the raw counts that the matrix sets up. When something like that happens, what you really need to do is write some functions so that out of the matrix you can create the percentages for the relevant cells, for the relevant rows and columns, which is very, very important and needed for you. Because then for a publication quality tabular presentation, you will need to present the percentages. And it will require a little bit of tweaking of the data, which I leave as an exercise for you now that you have had a fair bit of grounding in terms of what you need to do for your data analysis. Now this is about setting up a table. The next thing that you want to do is that these cells should be independent of each other. And that's very important because this is the heart and soul of hypothesis testing when you're dealing with discrete variables. For example, here we have got two discrete variables. The first variable is the variable called vehicle, which has got different types of vehicle representations like cars, LGVs, SUVs, buses, taxis, etc. And you also have another discrete variable, which is a factor level variable called helmet, in which it is stated whether the biker who is traveling by the side of that car or by the side of that vehicle, whether that biker wore a helmet or the biker did not wear a helmet. That is a factor level variable with two levels, zeros and ones. Therefore, both of these are factor level variables, the discrete variables and their categorical variables for which we would like to test the tests of independence. What is the test of independence here? We are likely to see, although it is not a very, very meaningful exercise, but for the sake of our argument, we'd like to see that, maybe vehicles, the kind of vehicle that the biker passed, may have something to do with whether the biker were wearing a helmet or not. You and I could argue that that may not be a very substantial theory, but even this is important to see that yes, indeed it was that our model, that is, this is not likely to be an important research question and therefore we are not going to be able to reject the null hypothesis, may play out to be true. How do we test that? One way to test that is to set up a chi-square test of independence. The way to set up a chi-square test of independence and a theory behind the chi-square tests of independence is this, that for each cell of this particular table, we will create an expected count. That expected count will be based on the total for the column and total for the cells. And then we'll see whether on the basis of the total for the columns and total for the cells, we can have an expected value that we can put up. So this is very, very interesting. Okay. So that gives us a sense of that. And then what we do is that from the observed with the expected, we get a square, and then we sum up the squares, and then we get a whole summated value for the chi-square. The way to do this in R is very simple. R's built-in datasets and built-in functions, which is the stats package, has a test which is known as the chi-square.test. When we were talking about the tests of significance, I showed you that in order to use these tests, all you have to do is to type the word .test, and before the .test, you specified what test of significance would you like to see here. So in this particular case, we are interested to see a chi-square test. And you store the results of the chi-square test into an object. And note what I have done. I have used it as a capital C HISQ. There's a little bit of thing that we need to explain here. You will see that in R there are many reserved terms. So chi-square is such a reserved term. All reserved terms in R are usually saved in the form of a lower case letters. So here CHISQ is a lowercase letter which it saves. If you want to save a distinct term which is not going to conflict with the reserved terms and therefore it's not going to throw you an error, you need to save it in the form of first starting with a capital letter and then the capital letter and the combination of anything else, you can save it as an object. So here, therefore, we have put together a capital CHISQ. That's the object to which we are saving the products of the chi-square test. Then if you order that you would like to really read what is contained within that object, R will put out a copious output of everything that's there. And that, in this particular case, is Pearson's chi-square test. It does not give you any sense of direction. For example, it does not tell you whether there is a monotonic increase in the row percentages across the rows. It does not tell you that. There is another set of tests called Cochran-Armitage chi-square tests of trend, which is not present here. It is a very plain, simple, what is also often referred to as a plain vanilla chi-square test. And here you see that it gives you the chi-square statistics. It gives you the degrees of freedom, which is in this case 6 because there are 2 rows, 2 columns. Therefore, column -1 is 1 and there are 7 rows. Therefore, there are like 7 levels of cars. So 7 minus 1, 6. So row -1 times column -1 gives you 6. So degrees of freedom is equal to 6. And if you, and I leave that to you as an exercise to see what is the area under the curve for a chi-square statistic of 6.44 with degrees of freedom of 6, you will soon see that the probability value of the probability distribution is around 37, so 0.3752, which means that that this is not an extreme outlier. In other words, you cannot reject the null hypothesis. In fact, if you rejected the null hypothesis, then the probability of your findings to fall under the null hypothesis is going to be around 38%, which is very, very high. It just tells you that these things are kind of independent of each other. So in other words, what car that was present and whether the biker wore a helmet or not are 2 events or 2 entities that were independent of each other. This is reassuring because when we did this and when we used a chi-square test, then we kind of knew that it was going to make sense because that was also a model. So our data fitted with our model. So we know that the data is good. We know that a chi-square test that we had employed was a good thing to do. I will next show you another test of independence where if the numbers are very low, so remember that in this particular case, you have almost all of them had like fairly big numbers in their cells. But what happens if your numbers are low? So you would need to have another strategy. And that strategy is called Fisher's, or it was the famous statistician Fisher's test of independence. And this has got a bit of a history to this. So what we are going to do is we are going to introduce this test of independence and see how it works. Now, Fisher, when Fisher kind of is often considered to be the father of modern inferential statistics because he did a lot of work on this. And what happened was that there was a very famous story that Fisher was challenged by a lady who claimed that she could differentiate between an event which may appear to be a little bit trivial now, but it was very important then. And that is, while making tea, she said that it would make a difference and she could differentiate whether tea was added to the cup of raw tea first, or whether milk was added to the cup of raw tea first, or whether you had a cup of milk to which tea was added. And she said that she could discriminate between the two tests of the same tea and the same type of milk. So Fisher, in the true kind of spirit of theory and kind of hypothesis testing framework, decided to test it. Therefore, he set up an experiment called t-testing experiment, which we have replicated here. And he took like 8 iterations of testing the tea before and after, adding milk to the tea, and before and after, then taking the test. So the truth was that milk was added first, and the guess was correctly done that there was that milk was added first or tea was added first, and the guess was also done like whether the tea was added first or milk was added first. So milk could mean that there was a problem with this, and tea would mean that there was a problem. But milk tea, so milk added first and then the tea would be correctly guessed. And we should see that the way this was worked, that the null hypothesis was this, that the taster would not be able to differentiate whether milk was added first or tea was added first. And the alternative hypothesis was that yes, the tester would be able to differentiate whether the milk was added first or the tea was added first. Because of the low numbers in the cells, Fisher devised a special test of significance for count data, and this was known as the Fisher's test. And in this particular case, we have put together that there's an alternative to it, because if the t-tester were able to differentiate that that it was the milk before the tea, then that would be meaningful in all cases, because either or does not make sense. In R, if you encounter low data and you wanted to repeat this test, the easiest thing to do is to use a function called Fisher.test. It's very, very simple and very easy to get that thing work. Then you put a parenthesis, or you open a pair of brackets, and then you put the object called t-testing there, and then put a comma and put alternative, and you say whether it's greater or lesser, the direction of this, and then you run the test. And then if you run the test, then it produces an output where you can see that the data will be given as a first line, and then it gives you a p-value. And that p-value in this particular case was 0.2429, which tells you that the findings that Fisher had, or at that time, was more likely to be under the conditions of the null. So you can see that p is equal to 0.25, so it was like 25%. That's the area under the curve of the Fisherian test that you can get to see. And of course, you could see that there was a big odds ratio of 6.40. That was quite big, but the 6.40 fell into a confidence interval that ranged between 0.31 to whatever. So you could see that there could both be either, anything would be possible in this paradigm, although it was centered around 6.41. Probably more likely that she was correct, but it was not very definite given 8 testings. Who knows what would have happened with more and more testing, but that's quite impractical. So this is one way of doing things. Okay. So now you have learned that there are 2 ways in which you can run these tests. One is you can use what is known as a Pearson's chi-square test, and you can use Fisher's chi-square test, or Fisher's tests of independence. Next, we are going to see that there are some omnibus tests that you can do by using a package called VCD. So install VCD if you have not already installed it. Then call the library, which is called library.vcd, And then you will see, and if you then use a function called ASSOC stats and then give the object of your table where you have the rectangular grid, it is going to put out the likelihood ratio, it will give you the Pearson tests, and Cramer's V tests, and it will give you the probability estimates for this. So we use the same things, you know, the old one where we were looking at the vehicle type and the biker's helmet, and once more you see that the likelihood ratio test and the Pearson chi-square test were very similar. In the next, I'm going to show you how it works out in real life. So here is a data set that you can get from the mass library, that is the mass package that we have been talking about. And this is about birth weight data, and there are a few other variables. We have only taken out whether the women were younger, older, what were their race, whether they were smokers or non-smokers, what was the exact birth weight of the babies that they had delivered. And then what we had done was that we had converted the age into from continuous data into categorical data, less than 19 years to above 25 to 20, above 30 years and above. That's sort of categorical. We have converted the smokers as non-smokers and smokers. We have converted the race from an integer variable into a factor level variable, so that now you've got like white, blacks, other races. And what's more important is this, that we have taken the birth weight, and based on whether the birth weight was 2,500 grams at birth, we have converted that into a binary variable. And now we wanted to model whether women who were smokers were more likely to give rise to lower birth weight babies. So we have used the mass library and we have used the xtabs function here. So what I'm going to show you are a couple of examples and see for yourself how we use the categorical variable hypothesis testing in real life. The first question we asked in this data set was whether the smokers are more likely to end up with small babies. The small babies were defined as those babies whose birth weight at birth was 2,500 grams or lower. So the way to do that is to invoke the xtabs function out of the mass library, and then what you do is this, that you put a tilde mark, put the explanatory variable or exposure variable first. In this case it was smoker, so the variable was smoke, then put a plus sign and then put the birth weight, which was binarized, and then put the name of the data, which is birth weight 2, converted birth weight from the original data set. And then the thing that you do is this, that once you have the xtabs, you can have a neat and printable output of the cross table by using a function called ftable. I could also have saved it as a matrix and then put it out, but I think this is a much better and neater way in which it kind of puts out the products of your cross tabulation, and you can see that the smoke WBW, which is the object, now gets put out as like that in a rectangular format. And then if you summarize this, then it gives you the Pearson's chi-square tests of independence, and you can see that smoking and birth weights are not two independent events, they are related one with the other. If you then use the rectangular matrix to calculate the birth weights, you will see that compared with the non-smokers, smokers really had a higher percentage of small birth weight babies, like 40% versus 29%. I will leave you to do the math yourself. We asked another questions. Are younger mothers more likely with smaller babies? Take a look at this. Again, we did the same things as before, cross tabs, and we had this time, rather than smoker, we had age rate plus the binarized birth weight. And again, you can see over here that there are a number of different, you can see the rectangular matrix. And I will leave you to do the percentage calculations out of this. but you can quite clearly see that the age of the mothers and the probability of developing a low birth weight baby, they're kind of independent of each other. And you can see here that a p-value is 0.24. Okay? So this is an example in which you can make some good use of how to read these data sets. So in summary, we have learned how to use the tests of association in R. We have learned that for discrete or categorical variables hypothesis testing, you need a matrix, which you can do using a table. You can generate very, very rapidly a chi-square test by just using the matrix and working through that. Fisher's exact test is a very useful test that you should be using this. And the ASOC stats from VCD package is particularly useful. And we have shown you that you can actually use a worked out example that we have shown you. You can very easily run some nice and practical tests of association with categorical variables. Thank you for paying attention.